Problem 1. Fill in the missing code for linear search. So, taking a look at this particular set of code, I can see that I've got my list of items that I'm searching for. That's called items, and the desired element that I'm looking for. Great. Okay, this is the start of my linear search. This must be the current position inside of this item list that I'm looking at. So I start at 0. I start at looking at this spot right here. And I want to continue until I reach the end of the list. So as long as position is in here and less than the length of the list, I want to keep searching. Since there are two conditions I need to look for when I've got my while loop. I haven't reached the end of the list and I haven't found my element. Well, to make sure that I haven't reached the end of my list, which is always the condition I check for first, then I take a look at this and I want to, while position is less than the length of my list, which is called items. And I haven't found my element. How do I know? Let's see. Not equal to the desired element. So I got half that condition set up. Then in order to figure out the rest, let's see. What's not equal to desired element? The item out of my list. Which item out of my list? The item at the position I'm looking for, because here's the position right there. Alright, then what do I do once I have that and I want to go to the next position? Inside that while loop I just got position plus plus. And now down here, the last part, have I found my item or not? Well, I know I have not found it if my position is equal to the length of the item list. If that's the case, then I've gone all the way through this loop. I have not found the item I'm looking for, and it is not found. Otherwise, it is found. And is it found at position I? No. What is holding the position of my variable? Position. There you go. Answer to number 1. For a linear search, if a list has n elements, in the best case, how many elements would the computer need to check before it found the desired element? That would be if the first item that it checked was the item that it actually was looking for, so that would be 1. Doesn't matter how large the list is, it would only need to check 1. If a list has n elements, worst case, how many elements would the computer need to check before it found the desired element? That would be all n. So if there were 100 elements, it would have to check all 100 if, in this case, there happened to be the element at the end of the list. If a list has n elements, how many elements need to be checked to determine the desired element does not exist? Well, with a linear list, starts up here, goes down, you have to check each and every one, so it would be all n. If a list has n elements, what would the average number of elements? Well, think about it. If you have about 100 elements with linear search, on average, it would kind of be here in the middle, right? So on average, it would be about 50. So we do n over 2. So the number of elements, like it was 100, divided by 2 in order to get there. So I'll cross this out so I don't mistake it for the answer. N over 2. Fill in the missing code for a binary search. Okay, great. Let's do the binary search. Here's our numbered list. Here's our desired element. Lower bound. Oh, what's the upper bound? Well, that would be the length of the list minus 1. The minus 1 comes from the fact that for a list of 100, we go 0 to 99, so I need to take that into account. Great. While, we're not done with the list. How do we know we're not done with the list? Well, as long as the lower bound is less than the upper bound, then we know we haven't finished yet with our search. If those boundaries cross, then we have not found it and it's not in the list. Okay, middle is int of what? Well, how do I get the middle? I need to take the lower bound and the upper bound, add those together, divide by 2. Basically, you're finding the average. So lower bound should come up with smaller variable names plus upper bound divide by 2, and taking into account order of operations, put another set of parentheses in there. And we're checking the middle position, so I know I need to check if my list, number list, at the middle position that I'm checking, so if number list at the middle position is greater than, we're going to move up the lower bound. Okay, so taking a look at that, I'm going to change my mind here. Let's do less than the desired element. Now, if you think about it, when I do this, I've got my entire list right here, and if this middle item that I'm checking in the middle position and my desired element is greater than that, that means my desired element's up here, so I need to move my lower bound up. So, yep, that looks right. Then I'm just going to do the same thing, but opposite here. Greater than desired element. Put some colons after these. There we go. Otherwise it's found, and that'll do it. Okay, so taking a look at this. For the binary search, if it has n elements, worst case, how many computer elements will it need to check? Then we want to do n base 2, log base 2 of n. So in this case, if you did 128, and if you did log base 2 of that, it would be 7. You could basically get it in 7 tries if you had 128 elements. Under what circumstances would a linear search work well, but a binary search wouldn't work at all? That would be the case as if the list is not in order. If you have an unordered list, the linear search doesn't care. Okay, moving ahead. Given the following grid of numbers, write code that would print the cell that contains the number 1. Well, I remember we always do row and then column. So where's 1? Oh, right here. And the row is 2. And the column is 1. So print. What's my variable name? I'm going to guess it's grid. Grid. Row 2. Column 1. That was easy. Write code that would set the cell that contains a 2 to the number 3 instead. Okay, well that one's here, so row is going to be 3, column is going to be 4. So I'm going to do grid 3. Hello, 3, 4 is equal to 3. Thank goodness I'm going to type this instead. All right, moving forward, write code that would set each cell to the number 5. Well, that's just a couple for loops. And we've got a 5 cells on both. So I just need to do for I, or I could do for row in range 5. That'll go from 0 to 4. For column in range 5, and then take grid row column equal to 5. Whoa, got a lot of 5s there. Moving forward, explain 2 points about the following line of code. Let's see. Creates class cat derives from parent animal. I can tell that from the code. Explain 2 points about the following code. Well, this is constructor. And let's see, calling the calls parent constructor. Assuming we're continuing from the animal class from up here. How does a programmer create his or her own library file in Python? Okay, well that's pretty darn simple. You save the file. Keep track of the name. And import file name. Something like that. Write a function that takes two numbers and returns the largest. Okay, so in order to do that, I just need to def f takes in two numbers, a, b, returns the largest. If a is greater than b, return a, else return b. Yeah, and if they're equal to each other, we'll just return that value. Write code for a function that will take in an array and set each element to 0. Def f my array. Now I can't do for item in my array because if I'm going to change the number, we've talked about that, we have to actually do the other type of for loop for I in range length my array. And then my array zero. Whoops. I is equal to 0. So I just go through 0, 1, 2, 3, 4 up to the length of the array, setting each item to 0. Write code that creates a class called cat. Give it one attribute and one method. Easy. Class cat. Name equals def meow and print meow. Not too hard, pretty straightforward. Write code that creates an instance of cat. Oh, okay. My cat is equal to cat. Remember, it's the name of the class that's up here. That class name goes here, open close parentheses. There we go. We've now created an instance of the cat. Set the attribute and call the method. So my cat dot name is equal to Pat the cat, and my cat dot meow. It's a function, so I need parentheses. There we go. And we're done.